Hello everybody. We're still talking about the phase diagrams for ternary component or ternary systems, where we have three components, and we discussed in the last time the lever arm principle, and so how we can calculate the compositions of a mixture that is a sum of two different mixtures, or a mixture that you extracted something from. And we saw that you can calculate the amounts from the distances on the graph, so you can get the compositions, or you can get the amounts based on the points that you have. And now we are talking about one important point that is really critical in the liquid-liquid extraction, which is the equilibrium between the phases. In most of the cases that we will see, or almost all of them, you would have an equilibrium curve like this, and this equilibrium curve is actually splitting the phase diagram into two regions: the region of single phase, which is a homogeneous phase, just one phase, and this is the two phase region, which is when the two components are not miscible, or are not totally miscible, might be partially or totally immiscible. In this case, you would find that there is this gray region, which is called the two-phase region. And what happens here is that the two components are not miscible, and so you would have any point here is gonna split automatically into two phases with different compositions. And this is actually what we need in our phase diagram, to have something like this to split the phase diagram into two regions, exactly like we do in distillation when we work between the bubble and dew point, or between the vaporous and liquid curve. So this is the envelope that we target when we do our extraction process. So it's critical, or it's very important to know how the phase diagram looks like in your system. So in this case, we would have B and C are totally miscible because you do not have any splitting on this line, and you have A and C are totally miscible because you do not have any phase splitting on this line. And we said that this is a binary system, this is a binary system, this is a binary system, and in this case A and B are totally immiscible, because you have the two-phase region covering all the length from 0% B to 100% B. So there is no way you would get A and B have any miscibility. It's like water and oil, for instance. They're never miscible. In many cases, you would have different, or for each case you would have different shape of the phase diagram. For instance, in some cases you would have something like this. You have, this is the one phase region, and the one phase region is covering all this area, as we said. And you would have here, for this line, B and C are partially miscible because you would have some miscibility here. A can dissolve some B and B can dissolve some A, but at this region they cannot dissolve each other. You would have partial miscibility. A and C are totally miscible, there is no phase splitting here, and there is partial miscibility between A and B in this region because of this envelope here. So this is how we read the phase diagram. An actual case is what you see here. It's water, chloroform, and acetone. The phase diagram shows that acetone and chloroform are totally miscible, chloroform and water are totally miscible, but water and chloroform are partially miscible because chloroform can dissolve some water here, but most of the envelope the envelope covers most of the region, except for this 1% at the very end, or yeah, it's at the very end of the water chloroform line. And this is how the phase diagram looks like. You would notice that there are some lines here, and these lines, we have not talked about them before, and these represent the tie lines, which are exactly like the horizontal lines that we drew on the temperature composition diagram for the wet region. And this is how the tie lines look like here. You would notice that they are not parallel and they are not horizontal, and that's why you will not be able to predict how they look like. Even if you know one or two lines, the slope of this is different from this, and this is different from that. So you'd never know how the tie lines look like, and that's why you have to have the tie lines drawn on the phase diagram, or to have tabulated data telling you that this is the relation between the two phases and this is how they look like. And as we said, in this region you'd have two phases, and these phases would be in equilibrium. And if you have a point M here, you need to know where is the tie line that passes by M, and then it extends from the right hand side to the left hand side of the curve, and then it will split into A and B. And as we said, you'd have any shape of the tie line, it would be with any slope. But the point that you need to keep in mind is that we talked before about the lever arm principle, and we can apply the lever arm principle here. So any point on this line would give you A and B mix, or like phase A and phase B with the same composition. However, the amounts would be different. So the amount of B to the amount of A equals this distance divided by this distance by the lever arm principle. And it would be different if M is here, and it would be different if M is here. So M is here would give a lot more B than A, and M here would give a lot more A than B. So it's important to keep in mind that the distances are different, and we will apply the lever arm principle almost every line we would draw on the curve would have a tie line or a lever arm principle calculations related to this line. One thing that's important to keep in mind when we do the liquid extraction is the temperature. Temperature is very critical when doing the extraction because it affects the two-phase region greatly. You'd see here this is a system of hexane, methyl cyclohepentane, and aniline, and you'd see that the tie line at 25 degrees Celsius, or the equilibrium or the two-phase region, is very wide here. It's taking almost 80% of the whole area of the phase diagram. And as you increase the temperature, the solubility of the components increase, and as you increase it more, the two-phase region collapses, and it collapses more and shrinks till it gets that small at 45 degrees Celsius. So only 20 degrees would change the two-phase region from this big to this small size. And of course, when we do the extraction, we would like to have a big two-phase region so that you would get as a big difference of composition between the two phases that you are separating. And this would lead to less number of stages than what you get from here. It's exactly when you have the equilibrium curve and the 45 degrees line in the distillation column close together, it would be something like this. You'd need a lot of more stages than if you have the equilibrium curve this away from the 45 degrees line, and then I'm sorry, from the operating line. So as they get close together, you would need more stages, and as they get farther together, you would need less stages than what we need in before. So it's favorable to be done at low temperature, and this is the point that I want to make, is doing this at lower temperature would make the separation easier and would require less number of stages than what you would do need at higher temperatures. One last thing I need to point out is that we have been working or discussing the three component system on the triangular phase diagram, which is the equilateral triangle that we have been talking about for 2 or 3 videos now. And this is how the phase diagram would look like, and we usually call or let's talk about this in a minute. But in most of the textbooks that you would read, that people would do all the calculations and all the drawings on the rectangular coordinates, which is the right angle triangle. You'll see that the right angle triangle is still a triangle, but they call it rectangular coordinates because it's right angled, and you have here these two look like half square or half rectangle. And the reason people the textbooks like to use this shape is that it's easier to put data and extract data from this more than this diagram. In this diagram, it's easily split into 10, 20, 30, 40 at 100, and this 10, 20, 30, 40 till 100. And you can draw this on regular graph paper. However, in this case, you have to keep in mind that this is not easily split into tens, and this requires some kind of calculations for getting exactly the 10, 20, 30, 40%. And if you have a regular graph paper, this is not one square, which is 1 centimeter. This is one, or it's gonna be less than one, because the one would be something like this, and this is kind of smaller. So doing the putting data and extracting data from here might be tricky, and there is a higher chance of mistakes and errors than working here. That's why people like to do this. It's exactly the same thing. You would have three corners. Each corner represents a single component, and you have lines. Each line represents a binary system. You would have and this equilibrium curve, and this splits the region or the diagram into one phase and two phase regions. Everything is the same. We usually call the C or use C for the solvent, A for the component that we are interested in extracting, and B is the other component that is not extracted. From this point forward, we are gonna work with this diagram, not this diagram. This was important for the sake of discussion and for the sake of understanding the basics and the concepts. Everything here is symmetrical from all the angles. But this is more practical and easier to use. So this is gonna be the diagram that we're gonna work with in the next videos. From the next video, we're gonna start working with the stage separation, and we will put the points and see how the points are located and how we calculate the output of the extraction process. And I'll see you in the next video, inshallah. Goodbye.